Welcome everybody. Thank you for joining today's live Lansmont product update. We will be showcasing sinusoidal testing on a Lansmont Model 10,000 vibration test system. This really is a unique opportunity to see this vertical vibration test system perform and get your questions answered directly by our VP of Technology, Eric Jonassen. As most of you know already, Lansmont is a proud member of the Physical Properties Testers Group, a collective of specialized brands in physical properties testing. PPT covers areas such as tensile and compressive strength, torque testing, textile analysis, and real-world dynamics like shock and vibration. So alongside Lansmont, our family of brands include McMesson, James Hill, and Telluras. To learn more about PPT or our individual brands, visit the PPT site or check out our on-demand content. A link is available in the chat box for your convenience. Many of you already know Eric, who's our host, and I'm Sharon Smarenberg, one of today's organizers, and we are supported by a dedicated team across the United States, Europe, and Asia. As with every single webinar, we really encourage you to ask questions. Throughout the webinar, you can use the question box to submit any queries you have, and we'll do our best to address these at the end of the session. The webinar is being recorded and you will receive a recording via the email that you registered with. And then please feel free to share this with colleagues who couldn't attend or who might find it of value. We'd appreciate that. And with that, I'll hand it over to Eric.
Thank you, Sharon. I'm going to go ahead and turn my camera on real quick. And there I am. So I just want to make sure I introduce myself once again before starting to get into the content, where I got some slides to share to start off the overall presentation or webinar. And then I'm going to spend most of my time on camera with a camera in my hand, walking around, showing you bits and pieces of our vibration test system, and then get into actually doing some, running some tests, sinusoidal sweep to identify resonance. We'll identify a couple different resonances on a little product I have, a product decoy set up on the vibration system back here, and show you that, how that all takes place. Try to move one of my other cameras once I turn it on in close to show you. Hopefully you'll be able to see the resonance, which I'm sure you will. I also have made my own videos of this separate from this webinar that I will, once we share this, the recording of this webinar, we'll also share those videos, focus much more specifically on what's happening on the vibration controller, the data that's being generated from the accelerometers that are attached to my decoy product back here. So I'm going to be going through a lot here. I'm doing it by myself, so I appreciate your patience. As far as presenting, running a vibe system, running a couple different cameras, walking you around. I'll try not to make anybody sick, but bear with me, and thanks again for taking the time to participate in this. I'm happy, and we move forward to expand on this. If anybody has questions or different ideas about going into more detail, I'm more than happy to consider that and offer future sessions like this. No problem at all. So I'm going to turn my camera off right now, and I'm going to go through a few slides before jumping into the walking tour of everything, okay? So, sine vibration. See a bunch of terms popping up on the screen here. This is following up on to an applications webinar we did, probably now about a month ago. Should have only been a couple weeks, but schedules mean we had to readjust when we delivered this. But I'm talking about sine vibration, sinusoidal vibration testing, and and so these terms that you see in and around the images themselves are terms that I'll be probably mentioning all of them in today's session, because they all deal with some way of describing either sinusoidal vibration or the responses that you see from putting things through sinusoidal vibration tests. So things like resonance, natural frequency, basically the same thing. Pitch is actually a different way from the sound or the music side of things of describing frequency. Frequency and pitch are basically the same thing. Tone is another thing that you can think of in terms of audible vibration versus what we see on a vibration test system, which is more of the dynamic side of it. But tone is a way of describing kind of what they call the warmth of vibration. And then we're going to talk about amplitude, which means how significant is the intensity of the vibration. We're going to talk about amplification and transmissibility. We're not just going to talk about it, but that's really one of the main things we're going to show from a data collection perspective. And then Q level as well, once we get to showing some data. I often, over all my time working at Landsmont, try to think of different ways, I guess, to trying to describe vibration, because sometimes people that don't spend a lot of time focusing on it, it's a struggle to maybe put your arms around. What do you mean by frequency, low frequency, high frequency, mid frequencies? And I always try to think of it in terms of sound, or describing it in terms of sound, because sound is vibration. So if you look at this just quickly, this sinusoidal signal that's on the screen right now, that's a 2-second time domain signal from left to right, and it's the amplitude is the intensity is the y-axis. So in this case, there's 2 seconds from left to right, and what that means is we're looking at a 2 hertz signal on the screen. And when we describe, like, what does that mean? What is 2 hertz? Why do I care about what a 2 hertz signal looks like? Well, you can think of it as in the world of transport testing or in simulation or package testing, it's low frequency. We call it a low frequency content. And when we say, well, low frequency, what does that mean? Well, if you think in terms of sound, you think of a way of describing low frequency as might be bass in music, or it might be rumble, the rumbling that you hear when something might be going down the road. So the low frequency is like the rumble content. If I put a different tone on there now, you see I just changed it. The orange sine wave is a 4 hertz signal instead of 2 hertz. So there's more of them, right? There's more peaks and valleys you see on the screen as compared to the 2 hertz. It's a higher frequency. It's happening faster. So how might we describe that? I'm not saying literally we might describe it as a rattle, but rattle is another way of describing vibration. And it's different. I would say it's a higher frequency description of vibration as compared to rumble, rattle. If I put a 10 hertz signal on there, there's even more of them. Now you see in that same 2-second window, there's a whole bunch of cycles of 10 hertz dynamic taking place. We might call that, a way of describing that as squeak. This is just another term for how people describe vibration. It's got a squeaky sound to it. And really high frequency content, not that 20 hertz, which is what's being shown in green, is really high, but the higher the frequency, another way of describing that is it's ringy. It's got ringing characteristics associated with it. So, we cover a range of sinusoidal tones from rumbly, low frequency, rumble, to high frequency, ringy kind of content when we perform this type of testing on a vibration system. And again, this is, maybe some people remember this is my time back in high school and college, graphic equalizer. This was a graphic equalizer, something that might display on your audio equipment. And you would see this, right? And what this really is left to right is frequency. Those are different from the left to right. It says 63, 160, 400, 1000, 2500. Those are actually, that's hertz. It's very similar, it's frequency, but it's really the audible frequency bands that we think of. And this is what, just that same idea as far as when you, instead of just seeing how the sound is playing back, this was something that you could use to adjust the sound. So those sliders on the left and the right, each and every one of those sliders was something that you could shift up or down depending on the content that you wanted to hear from your music. So the left-hand side of those sliders means low frequency or bass. If I wanted more boom, boom, or bass or rumble, to my music, I would push those levers on the left-hand side of both the left and the right audible, the stereo sound. I would push them up. If I wanted less high frequency, more ringy treble kind of sound, I would push those sliders down. And this will, one of the upcoming webinars is going to be talking about random vibration, where this also has a play in trying to understand how we look at vibration in terms of the random content. But that gives you an idea of frequency. When we think of frequency, you can think of it in terms of sound. So back to our world, which though is originally the physical or the motion, vibration testing, sinusoidal motion that we're doing in our laboratories on our machines. Why do we do it? Why do we use it? What value does it have? Does that happen in the real world? No, not really. Not necessarily the way we do it on a vibration machine. We use it to sweep through a range of frequencies where we can document how products or components within the product respond to that input. And where those products or components have the peak response throughout that frequency range, we call that resonant frequency. And again, we'll show you what that looks like here in a minute on the machine. And that motion, that resonant frequency associated with the motion is indicative of where and how products or components on those products would experience damage, or where that may occur. It doesn't necessarily mean it's going to occur, but if there's going to be any damage occurring as a result of vibration, it's very, very likely it's going to be associated with where the product gets excited, which means the resonant frequency or frequencies. There might be multiple frequencies where it gets excited, but that's where it gets excited, and that's what we're trying to identify by doing the sweep. It's important to understand where those frequencies of excitement occur. And then what we do is we use those answers or those resonant frequencies to perform what we call dwell testing. So once we identify that natural frequency, then we have the ability to go set the vibration machine to sit specifically at that frequency, no longer sweeping between frequencies, but sitting right at that frequency and shaking at that worst case scenario, at that worst case motion. And it might range. People might run dwell tests for 10, 15, 30 minutes where it's sitting at that frequency and the product is exciting, moving quite a bit usually, or the component. And that's a good way to assess whether that resonant frequency is or likely going to be a source of damage. Again, just because there are resonances doesn't mean they're going to cause damage, but if damage is going to occur, it's at those frequencies. And so one of the ways to really push the envelope on that to say, I found a resonance, but will it be a problem? Well, the way to answer that question is to dwell at that frequency and see if something breaks, changes, loosens, abrades, so on and so forth as a result of that motion, okay? So quickly, just as it relates to the vibration systems, because I'm going to walk a little bit around the vibration system before I actually run the vibration. So, from a user perspective, when we talk about our vibration systems, how do you go about picking one? Like what is the right vibration system? We obviously make a number of models. Other people in competitors or whatever, other people that provide vibration systems, have different models, right, with different performance criteria. And so how do you specify what the right one is? Well, for us, there's basically two key criteria, which is how big of a test article, with you might call those DUT, device under test, or how big is or are the items that you intend to test on that piece of equipment, meaning the size, the footprint, how big of a place does it need to sit on, and then how heavy is it? How big and heavy is it? That's one of the big main key criteria, because that helps us determine how much oomph, power you need to move it and shake it. And not only just to move it and shake it, but also what kind of performance do you need? Meaning, what are the test profiles, really? What's the frequency range and what's the test intensity that you intend to be using or putting your DUT, your test items, through. And that's, can be described in a couple ways. It's obviously, again, the frequency range, maybe for sign sweep testing, or the frequency range from what type of environment you're trying to simulate, like a transport environment, truck, over the road trucks, trains, airplanes. And if there are industry profiles, that's the other way of describing the performance you need. You need to do ASTM 4169 truck. Do you need to do ISTA 6 Series Amazon vibration profile, or Sam's Club, or UPS, the 3A, or FedEx, the parcel pickup and delivery profiles? Those all help us determine, for instance, what to recommend in terms of the sizing of a vibration system. And how do we do that? Just quickly, is just to remember that all of this stuff that we talk about, G level, displacement, G level, velocity, and displacement, are all related mathematically. So if we have an acceleration versus time signal, if we integrate that signal, we're able to calculate the velocity associated with that time domain signal. And if we integrate that, the velocity, we can calculate displacement. So all this stuff is related. And it's not only is it that important to understand, but it's important for us because we use that to drive, like I say, how we recommend test systems. So what this is just a short video showing you one of our modeling applications, right? We use a modeling application where we have tons of data from our 50 plus years of providing these systems of how certain configurations of machines perform, meaning the size of the tables, the size of the actuator, the size of the hydraulic power supply, which I'm going to show you literally here. But we have all that stuff in our, you can imagine a large database where we're able to pick and choose and say, all right, if you have this, you're a customer that has this 2,000 pound, 1,000 kilogram test item, and you want to do the ISTA 4AB air profile, we can plug that in and we can configure systems and predict whether they're going to run or not. And not just run, but meet the demand that's required to run that test. So we use all that information to help specify these things, specify what we put into our recommend putting our customers into. Quickly, key components of a vibration system, which I'm going to walk around and show you a little bit. But seismic base, the table, the actuator, the hydraulic power supply, we refer to those as HPSs. Those are all critical components in putting together a vibration system. Why is a seismic base important? Well, it's because it's what helps to keep the vibration that's being performed on the tables from being transmitted through the floor into the building, into the surrounding environment. It basically is there to absorb as best it can the energy from being transmitted outside of the test. Let's put it that way. And so it's really critical, the sizing of that. And there are relationships or rules of thumb that says if you're going to test something of X mass, then your seismic base has to be, let's say, 5 or 10x that mass in order to work properly so that you're not disturbing anybody in the lab, in the building, in the floors above the laboratory. The table obviously is critical, not just from a size perspective, but because the table, all of these pieces, we're talking about things like sinusoidal vibration testing and resonance. All of these things I'm talking about have their own resonances, right? Everything does. Everything has the potential to have natural frequencies that you need to be aware of. Tables do as well, right? So the bigger a table, the less stiff it might become. Something that's 5 feet square versus 2 feet square, you can imagine, or 6 feet or 7 feet or 10 feet square. The bigger that becomes, the less stiff it may become. And the less stiff it may become means that it's going to start developing resonances where the table actually starts to flex and bend. You might not, you would not be a flexing or bending that you would see with your eyes, but you could measure it. So it's really important that you avoid those resonances, or you design your tables so they don't have resonances in the performance range that you need to perform your testing. And so there's a lot of, again, design that goes into tables to make them stiff within the right frequency range, and then putting that system cable on on top of an actuator, which is the next item to the right. That's the piston, right? That's the piston that makes the table move up and down. So that actuator is mounted to the seismic base on one end, and it's coupled directly mounted to the table on the top end. So it's what causes the table to go up and down, move up and down. And obviously, you move up and down where you can see it visually, but also move up and down at super high frequencies, all simultaneously, that are part of any test profile, whether it's sinusoidal or random. So that's a critical thing. And it's in the actuator, the size of the actuator, not just the height of it, but even the diameter of the piston that moves up and down. That's important. The more force you need, or the bigger, the heavier the mass that you're going to shake, and the more extreme the profile that you're going to try to run with that heavy mass, means you have to have potentially a bigger, more robust actuator to be able to handle that load and move that load. So there's a range of actuators that can be supplied depending on, again, what the size of the test item is, and what the mass of the test item is, and what the profiles you need to run. And then last but not least, but the hydraulic power supply, the pump. So the pump sends oil through that actuator, to that actuator, through a servo valve that's attached to the side of that actuator. And that's where you get the power. They're called hydraulic power supply. That's what provides the power to make the thing move up and down. And the more it has to move up and down, especially with, let's say, low frequency, more stroke, we call it, the up and down literal displacement, the more it has to move up and down, the more volume of oil required to do that, or to cause that motion, especially with not just moving it, let's say, 4 to 6 inches, but it might be easy to move something 4 to 6 inches, but moving it 4 to 6 inches with some amount of intensity, or almost think of it as a violent motion. If you're trying to simulate a really robust motion, you need a lot of power to do it. So those are all the key kind of components. And then obviously the controller. The vibration controller is the other key component that is what controls where you save setups, and you recall those setups, and you drive your vibration system to do, and what we're talking about today is sinusoidal vibration testing, sweeping and dwelling, or random vibration, which are the two primary modes of testing that people in our sphere, customer sphere, use, is sine sweeps, dwells, and random vibration testing. And there are a number of different types of vibration tests that can be performed, and all that is handled by the controller. It's key, obviously another key component, okay? So I'm done talking, or I'm going to keep talking, but I'm done presenting on the screen. I'm going to switch my camera back on my laptop. I'm going to stop presenting here. And Sharon, maybe you can just help me to know that I'm
I can see
good.
you, Eric.
Okay,
Good.
So bear with me, everybody, as I get my other camera fired up. Multitasking here. And tell me if I'm good.
Good to go.
All right, so I'm going to walk around now. I'm going to leave both cameras on. I guess the other camera just gives you an idea of my size or perspective to this machine. So I'm going to do a walking tour of the vibration system here at Michigan State. As Sharon mentioned, this is up for us what's called the Model 10,000 10K vibration test system. And in this example, as you can see in both videos, I was looking at the wrong one with my hand. I apologize. You were looking at nothing there, but this is in a pit. Okay, these vibration machines, obviously, many of them, I'd say most of them that we sell, are not mounted in a pit. They're on the floor. They're mounted on a shop floor, which is, no problem. Usually even a 6-inch standard floor. Sorry for the English units, but 6-inch floor, standard shop floor or lab floor is all you really need for one of these machines, because the seismic mass itself, which I'm going to go down and show you in the pit here shortly, that does the job of absorbing all the energy. You don't have to worry about it so much. The nice thing about being in a pit like this is that you can see the floor approaching the pit. You can drive a forklift, right? And so if you're testing big, heavy loads, which they do here because this is a relatively powerful vibration system, they can drive a forklift close and load that, or a pallet jack, forklift, get the load close. They don't have to have the load sitting up in the air, maybe 5-6 feet in the air. It's something that can be close to the loading level, and then it's also can be beneficial because then you can walk up to it and observe the testing that's taking place. If we had a pallet load of something or a stack of boxes on there, it's kind of at your level, so it's nice. Pits are nice. They can be expensive. And once you're committed to it, it's less desirable to relocate if you ever plan or have the option to relocate your lab space or the machine. It's not an insignificant thing to be left with a big hole in the ground. But this is a pit mounted. It's very nice. So there's not a lot to see here. As we look at it floor level, you see the controls in both screens. So this is the vibration controller over here on a cart that's attached to it. A lot of cables that are going between this cart and the machine itself. And I'll show you from the back side at some point. And in this case, they have a nice display up on the wall that mirrors the controller, so they can use that for teaching and demonstration when people are coming through the facility. So I'm going to walk around. Bear with me. It should be pretty stable as I walk, because I got to get down in the pit from the back side. So I'm going down the stairs here. And again, I hope this is visible as I come down these stairs. So now you can start to see as I get down the pit when we talk about seismic mass. Okay, so bear with me. I don't think I can do a wider perspective, but this is the seismic mass, and you can see these big shock absorber guys that are mounted to the outside or perimeter of the base. They are attached to keep the base from walking, to actually moving from its mounting position. They're called dampers, and they again help to minimize the amount of reaction that the mass will have during testing. And I'm going to lower this even down here. I'm going pretty low, and you can kind of see there are, it's almost impossible to see, I guess, but everywhere there's a bolt hole here. There is what's called an elastomer pad underneath the machine. So it's actually sitting on an elastomeric material that's attached or coupled to the base itself. And that's another thing that helps to isolate the vibration from being transmitted into the floor, or allowing the base to shake too much. Because imagine the vibration mass has its own natural frequency. This whole system does. And so it's got a frequency that it likes to shake. And we can tune that frequency by selecting those elastomer pads. The more springier, the softer, the lower the natural frequency of the base, the stiffer, the higher the natural frequency. And there's reasons why you would want one or the other, which is basically to decouple the energy from being transmitted into the building. But they are definitely tuned a very specific way for us. And so as we go from the seismic mass upwards now, I'm just going to show you what these guys are here, are what are called 1G supports. Basically airbags that are attached to the underside of the table. So air flows through these guys, just shop air, plant air, fills these bags up. And what do they do, or what is their purpose? They're basically just there to support the load, to make it easier on the actuator itself that's driving the system. It makes it less of a workload on the actuator if you can basically make the whole load float. and supporting the load. Not all of the load is taken by the actuator. So the middle column, though, that is the hydraulic actuator. In this case, that's a 10,000 actuator for us, called a 10K actuator. You can kind of see the chrome inside there. That's the piston that moves up and down. I'm on the back side of it, so you can't see the servo valve right now, but if I change to the other side, take a seat, you can see the servo valve on that aluminum manifold. So that's the servo valve, and you can see the two big black hoses that are coming into it. That's where the hydraulic fluid comes in from the hydraulic power supply. That flowing through there is what makes it go up and down and do all of its magic. And it's all controlled by the servo valve. The servo valve is really the key thing that tells the actuator to go up, down, at what frequency. It's where the magic happens. It's through that servo valve. And I'm not going to necessarily show the hydraulic power supply, which is in another room. It's in a closet next to the lab here, but you can see that trough over there. See, yeah, right there. That's where all the hoses, the hydraulic hoses, are traveling through that trough into a room on the other side of those doors that houses the hydraulic power supply. So that's everything I was going to show you there. I'm going to go back and I'm going to run it now. Run a test. What I'm going to show you before I do that is that what I have set up here is a dummy demo product. So it's a product that's rigidly coupled to the table. So you can see it's actually tied down rigidly to the table. And then what I have is a beam. I have a beam with a mass on top of it. And that beam is basically simulating a spring mass system, right? It's a modeled spring mass system. It's because that beam acts like a spring. It's suspended, cantilevered out. It's got a mass on it. And then what I've got is an accelerometer, a vibration specific accelerometer. That's a big one. Yes, normally they're smaller than that, but it is a vibration accelerometer specific. You can have different types of accelerometers that are geared more towards shock applications, high G applications, or vibration. This is a vibration sensor, obviously, to be used on a vibration test system. So they're more sensitive, they're more capable or appropriate for measuring low intensity signals. So this is a vibration accelerometer. See the white cable that runs back over to the, I'm pointing in the other camera, to the vibration controller behind me. It's plugged in there. And what we're going to do is we're going to run this table through a sweep, and we're going to sweep it, and we're going to collect data from that very specific position and see if we can't identify, see what resonance looks like in terms of the visual, how much that is actually moving or dancing, but also then what that looks like in terms of data. So I'm going to show you all that moving forward. I think I'm going to move my this camera. I'm going to leave it here as I'm running the test, or close. So you're gonna have to bear with me as I change my little tripod setup. But I'll leave this camera right in front of the demo product, so you can hopefully see it. So bear with me. Okay, I'll make sure that I'm pointed at it. I know I'm not. Sharon, looks okay, basically?
Yes, that's good. Thanks,
okay.
Eric.
Thanks. Okay, so I'm going to walk away to the controller and I'm going to start this. So what I'm going to do is the table is now going to start a sine sweep, and it's going to start shaking at 3 Hertz. So the table is going to be moving up and down at 3 Hertz with a constant acceleration amplitude, basically the intensity of a half a G. And it's going to start at 3 Hertz, and then it's going to sweep upwards to 50 Hertz. In this case, I'm only going to go to 50 Hertz. That range on this machine like this can go anywhere upwards of 50 to 200, maybe even 300 Hertz. But since I know where this resonance is going to end up, I'm only going to go to 50 to save time. So it's going to start at 3 Hertz, slowly increase in amplitude, or excuse me, in frequency. And I just hit the start button. You should see the table rise up. It just came up. And now it's going to start moving up and down. And there we go, shaking at 3 hertz, meaning the table's going up and down 3 times a second. And it's increasing, so it's already upwards of about 4 hertz. Okay, my guy keeps changing a little bit, so I'm trying to adjust along the way. But you can see me going now, or see it going here. And we are at 6 hertz. So I think this happens about 15 hertz. On the controller, I'll eventually bring the camera back over, but what I'm plotting on the controller, if you can see maybe up on the screen here, is a blue signal trace that's starting to deviate from the white line. This blue trace is deviating from this white line, and this blue trace is a trace of that signal coming from the accelerometer that's on the end of that beam. And obviously it's going up and up and up. And if you can see on the camera, it might be hard to see even with the camera that's close to the widget, but right now it's in resonance. It's shaking quite a bit. And now it's coming out of resonance. It's still shaking, it's still excited, but it's less excited. And it's coming down and will continue to go down below that white line. And we're at 25 hertz. So we're going to 50. It's speeding up, so we'll be at 50 here shortly, and then the machine will stop. I'm going to grab my camera when it does. Actually, I'll just go ahead and stop it right now. So if I stop it and I grab my camera and bring this over to the controller, this is what the data looks like. Okay. And so when we look at this, the y-axis on this graph is acceleration. The x-axis is frequency. Okay. So we started at 3 hertz here. This is 50 hertz here. And at this point, this is indicative of where the item went into resonance. And if I want to understand where that is, I can use analysis features to basically drag a cursor over it and identify it, sit right on top of it, which says that's about at 17, 16 hertz, or I can have it auto analyze it. And I'm just going to right now click on it. And so I just clicked on that frequency, and what it did is it set cursors to the left and right of it, which basically identify a zone of amplification, or the amplification zone, basically where the amplification exceeded 2 times the input signal. So right now I'm showing acceleration, specific acceleration level in G's. So the table was shaking up and down throughout that whole test at a half a G, which is this white line. But at this resonance, my widget at the end of that dial there was shaking at 1, 2, 3, 4, 5, about 5 G's. And so what does that mean? Well, it got so excited, even at that same frequency, it was shaking at 10 times the input acceleration level. And another way of graphing that is to switch from what's called the acceleration view of this plot to the transmissibility view. So now, it might be hard to see it, but that says transmissibility. And now it looks the same as far as the sweep itself and the shape of the curve, but the new numbers are different. See, so now it says 10. So this is a 1-to-1 ratio. So that basically means when you're going through a sweep and the accelerometer on the widget is seeing the same response as the table is putting into it, you have a 1-to-1 response. I feel the same thing the table's feeling. But as I get excited throughout that frequency range, and where I see the most excitement is, I was shaking at 10 times the amount of energy or motion as compared to the table. And so that's indicative of resonance or natural frequency, okay? So what I'm going to do right now is dwell at that frequency. And so you can see what that looks like. So if I go ahead and start my test again, Now I'm going to change my view to what we call manual controls. I can go to the frequency controls. Instead of allowing it to sweep it like it's doing right now, I can pause it and I can come here and set a very specific frequency. And I'm just going to go right to the, which was 16 hertz, and say set frequency. And now it's the table's shaking. So I'm going to move you back over here, walk you down, take a look at the table, and you can see the guys dancing, right? I hope, and it's hard sometimes to know how well that shows up in video, but it's moving quite a bit. And again, it's moving 10 times more. You know, if you look at how this is moving, that they're both shaking at this 15 hertz or 16 hertz, but that's moving 10 times as much as this is moving in this vertical direction. And so this is where you might sit here and dwell for at that frequency for something like 10, 15, 30 minutes to see if and when this might break. And the last time I did something like this, it did break. Just think of the old taking a credit card. If you want to break a credit card in half to throw it away, what do? You bend it back and forth a number of cycles to the point, at some point where you cause fatigue, you break the fibers in the material and it breaks, it cracks and falls apart. And I'm sure if I left this running long enough, the same thing would happen here. So that's a dwell at that frequency. Now what I'm going to do, I'm going to set this down. I'm going to stop it. I'm going to do one last kind of quick switch over on the test item itself. Okay, crawling on the Vibe system. All right. What I'm going to do is I'm going to change this beam. Okay, so what I have is a different beam in my hand. This beam is about half the length of the one that's currently being used, and I'm going to switch that out. I'm going to switch this mass over, take the mass off of this beam. And I'm going to put it on this beam, this shorter beam. So the mass is staying the same, but the beam, which is the spring, is cut basically in half as far as the distance. And then we will repeat that test. And we will collect our data and see if and how the resonance changes. And so I guess what I would say, maybe a lot of people, it's pretty basic to them. They understand this clearly, but what happens when things are shorter versus longer in this scenario? So the spring got shorter. Well, that means the spring is going to get stiffer. This is going to get stiffer. It's still going to have has a resonance, but it's going to change because this beam, instead of being this length way out to here, is now shorter at this length. So that's one of the ways you can address resonant frequencies if it's a problem. It's one of the ways to try to change it, to stiffen it, or change the frequency one way or the other, is to change the product versus dealing it with packaging material. So now I'm going to repeat this test. Okay, so now I've walked back over to the vibration machine and I'm going to start the test. We're going to do another sweep. I will move this camera in once again a little bit closer. And if you look up here, and I will eventually bring my camera over back to the controller to show it, but you can see on that plot, I don't know, I'm pointing at, you can see the marker from the first resonance. So it's still there. The horizontal, or excuse me, the vertical line with the amplification zone is still on the plot, but now you see the new trace is passing through it up there from left to right. And so as we approach the resonance of this different, stiffer, shorter beam, we would expect that the natural frequency to be past or to the right of the first run or the first test. So it's starting right now to show a little bit of excitement, not a lot. And we're about to pass through the 16 hertz, which was the resonance of the first beam. So you can see it just passed right through there with very little amplification at all. Nothing to even be concerned about. And now it's coming up. We're at 25 hertz. Next major line is 30, the division on the graph. And now it's coming down. So I could stop it, quite frankly, there, but you can see we've now got a new resonance that's been identified. And if I stop it and I go to my analysis and I take a look at where that is, it's basically 30 again. Yep, 30 hertz. I can click on it. It identifies that range. So we actually, by cutting the beam in half, we stiffened it twice as much. So we changed the spring constant of that beam from having a frequency of 16 hertz. Now we're out at 30 hertz. So I'm getting closer to this point. You can see the difference. You know, here is the new stiffness is 30. This is 16, basically half. And if I do the same thing with this and I start the test again and I want to dwell at that frequency, I can display my manual controls and go to the frequency controls. I can say hold it once it starts moving, dial in or enter in 30 hertz, set it. It's shaking at 30 hertz, and it's less obvious when you come and look at it because the higher the frequency, the less the overall displacement is. But if you look closely, I think anyway, you'd be able to say I definitely see that it's wobbling around. And you can see the cable shaking quite a bit because of that frequency. So this is really dancing, and if I feel it compared to what's, you know, if I feel what's happening at the table versus what's happening at the weight, it's obvious the amount of excitement or delta that's taking place there due to that resonant response. Okay, so that's how that works. I'm going to turn this one off, Sharon, real quick, because I know time is of the essence. I'm going to stop. So now that's turned off. I'm going to go back to my computer real quick. Going to turn my camera off here. And I'm going to share my screen. Actually, I'm going to just come on camera real fast. I think too many things going on my screen. Apologize. So I'm done with the kind of the tour, walking tour of the machine, kind of how that whole idea of sign testing, sweeping, and dwelling works. Because of the interest of time to move forward and just talk about what I'm going to be doing next. I'm going to share that on my screen. So I'm going to show my screen. I'm going to turn my camera off and just want to mention that what I'm going to talk next about in January after the first of the year is random vibration. Random vibration is more of what we all use with these machines to simulate the transport environment. To simulate the transport vehicles, the mode of transport, trucks, trailers, vans, trains, intermodal containers, aircraft, big aircraft, little aircraft. We use what we call random vibration test profiles to simulate that. They look something like this, which again, I'm not going to get into the detail about this. This is what I'll be talking about in the next 2 webinars that we're hosting. When those take place, they take place. The first one, just talking about random vibration application, January 15th. And then 2 weeks later than that, we're going to be back in the laboratory here talking or showing the use of various random vibration profiles and how you go about programming those in and what you're seeing from that perspective. So with that, I want to say thank you. I'm going to turn my camera back on. Sharon, I will ask for your help just to let me know if there's any questions that I could answer.
Thanks, Eric. We've got one question already, but let me just invite everybody that in case you have a question and you've not yet put it into the question box, then now is your time to do so.
And
so,
thanks for sticking with me with all that moving and dancing around.
So the first question is, can we use two sensors, one on the product and one on the shaker, for measuring transmissibility?
Yes. Yep. That's exactly how transmissibility is calculated. So there, I didn't point that out, but the transmissibility in what I showed there was when I said it was a 10 times amplification factor. That's way of describing transmissibility. And so the way that's calculated is dividing the response of the widget, the beam, on the table by the accelerometer signal that's on the table. And right now, I didn't show that when I was doing the tour, but there is an accelerometer, basically just like that, on the bottom side of the table. And we call that the control accelerometer. That's what's used by the vibration controller to make sure the table's doing what you want it to do. Meaning it maintains the G level of the table. So when we say we're shaking the table at a half a G continuously through that sweep range, 3 to 50 Hertz is what I did here. The control part of that, of the intensity, that half G, is being monitored and controlled by the sensor on the bottom of the table. So we basically just divide the response signal from this sensor by the input signal from that sensor, and you can combine multiples. You can have, as many as, like in this machine here, they can have 8 total channels. So you can have a number of sensors. This is a simple setup, but if I had a pallet load or a product, a very sophisticated product full of electronics, like a server rack that might be as big as this whole table footprint wise, but as tall as me or taller than me with lots of expensive equipment in it, you can have sensors all throughout that cabinet and measure the responses everywhere, measure the amplification between those locations in the table, but also between one another, if that makes sense. You can understand how one is shaking in reference to the other. All of that is just math, easy math to do by the controller itself.
Thanks, Eric. Then, do you offer a software to check for resonance frequency of jigs/products?
We don't do, we do that when we're doing field studies. Let's say, so because, even if you're using, let's say, a Landsmont saver or a shock and vibration environmental data recorder that you send out in a decoy package like that, but if I had that this was going in a box and had a data recorder mounted to it, we do measurement in our own labs, our own capabilities, even in our headquarters in Monterey, to try to understand, define or characterize that decoy itself that might go out in the transport environment. But because you can imagine, depending on who you are and all the different products that you may have, especially in the consumer electronics world, let's say, that's a specialty, right? And there are certain companies and people that do that very well, that design those fixtures, and you have to be, very adaptive. It just depends. It could be medical devices, consumer electronics, displays. So we don't really offer that, but the technology is used certainly to define that or to characterize that. And it's not just even characterizing it from a vibration perspective, but even from a shock perspective. Both of those are important to make sure that your fixture isn't adding or subtracting any of the dynamic that you're trying. You don't want this. So the table's putting in one frequency, and you want that frequency, like in this example, to be transmitted directly through this product, which is why this product is rigidly coupled to the table. You don't want this product fixture being, impacting the reason why this is resonating or going into amplification. So one way or the other, it's good to characterize every bit of your setup so that you understand, the dynamics, the responses. What is it that's really shaking? Is it the component that's shaking, or is it the body or the decoy or the fixture? Maybe that the person is asking about, is the fixture the source of my resonance, or is it the product that's the source of the resonance? So yes, understanding all of that very clearly is important to allow you to assess the testing results correctly.
Thanks. Next
Yep.
question. During the sweep, after the point of resonance is reached, why does the response decrease drastically, even to a level below the input level?
Yeah, that's just normal, and it's not just even that that the products like this. Unfortunately, let's see if I can call. I don't think I can call it back up right now. Sorry, but it decreases because the vibration energy frequency is so high that the widget or the beam or the product, or in many cases, let's say it's packaging, right? This is that right here. We're testing a dummy product with a dummy spring mass system. But the next thing that you would be able to do in this is that you use this information for is to design potentially protective packaging. That packaging material, if you're really using this all to its advantage on the design side, is the packaging material attenuates any of that energy from, like in this case, this is 30 hertz where this resonated. Well, if I was designing a packaging system, transport system for this product, I'd want the packaging to have a resonance at half of this frequency or below. So in this case, this one, the shorter beam at a 30 hertz resonance. I'd want my packaging material, if I had foam underneath here, and I do have some foam, need another hour for that presentation, but if I packaged this with foam and it was tuned the right way, that foam itself would have a natural frequency of 15 hertz or less, such that it would never let the energy be transmitted through it, vibration energy through it, at, let's say, greater than 15 hertz. And so what happens on the plot, like the attendee said, it drastically declines. And when it does decline, it declines, if you can kind of see it goes below this 1-to-1 line. And so when it goes below that 1-to-1 line on that plot, that means that it's actually responding less than what energy is being put into the table. Above it is amplification, below it is attenuation. And so that's how packaging materials work, right? Is they attenuate things. And so that's actually really critical. Think of it as like noise cancellation. I'm using earbuds for this. I muted myself, sorry. But they work to cancel out, they don't let energy through. In earbuds, they don't let sound vibration or energy through. Packaging materials, they don't let dynamic energy through, vibration energy through the materials into the product because they attenuate it. They're not able to respond mechanically to that energy. They just can't respond. That's because it's outside their frequency component characteristics. I don't know if that's a good answer or not, and if somebody has more questions about that, I can show that in a number of different ways in an email or a subsequent conversation.
Thanks, Eric. I think
Yep.
that is all we have for now. I have in the chat box put links to both of the random vibration, the applications webinar, and the live product update. So if anybody's unsure, where to register, that would be the place to do it. And like always, if you have any further questions that were not addressed here today or that you think of later on, please feel free to reach out to Eric directly. It's eric.jonassen@pptgroup.com, and he will be more than happy to give you more information. But thank you very much for joining us for today's webinar, and we hope to see you for the next two as well.
And like you said, Sharon, obviously this recording will be posted and circulated, the recording of the webinar, but I will make sure to have some additional videos that were shot without movement and better quality videos of what was going on behind me with the table and the controller that we can share to supplement this as well. So again, thanks. And I guess I would say anybody who's still on connected, have a happy holidays, have a good break, enjoy yourselves. Look forward to seeing anybody that is interested in attending the next sessions in January after the first of the year.
Awesome. Thanks, Eric, and we hope to see you all for the next one. Have a good day. Bye-bye.
Thank you. Thanks, Sharon.